All right, good. Have everybody's attention. I want to introduce our speaker for today. And like I said before, there's sign-in sheets floating around, and there's also I sent out a survey for the physics club. We're trying to get that to everybody who's taking physics classes. So some people who may not be in the physics classes or may not be students here or maybe alumni, we'd still like to get them to fill out the survey. And for those who don't fill out the paper copy, at least there's a copy online on the Facebook page. Today's seminar, this is our, one tradition we've got here is that every time we get a new faculty member, they have to give a talk at the seminar series. And so today our new faculty member is Dr. Paul Withey. He came to us from Northwestern University in Louisiana, or Northwestern State in Louisiana, where he was the chair of the physics department there. And he is our new associate professor of physics as of last fall. And he's been doing some work with Rice University on applications of carbon nanotubes. And he's going to be talking about that today. And this is also work that he's been doing for, a couple of years you've been collaborating with him? Yeah. And so he's going to talk to you about that. And then also he has been teaching several courses at the undergraduate and graduate level. And this semester he's teaching the graduate statistical mechanics course. And then he's also been teaching our university physics class, and he's taught astronomy here. And so he's, you'll see him in and around a lot of different courses, so you might as well just get used to him now. So anyway, I'll turn it over to Dr. Withey.
Okay. Thanks, David. What I'd like to talk to you today about is some of the research that I've been doing on carbon nanotubes. Is there a way to swap over from here to here?
Yeah, just turn it off.
There we go. All right. Okay. So I'd like to talk to you a little bit about carbon nanotubes and some of the research that I've been doing, trying to get these things into different materials, into epoxy, and then some of the problems associated with it, and some of the new exciting developments that we've got. So, sort of a brief outline. I'll go over a little bit about what carbon nanotubes are, what their properties are, how you identify them, and then we'll look at fluorescence. I've been specifically looking at nanotube fluorescence, which was discovered by Bruce Wiseman in his lab in 2002. So it's very interesting development in terms of you can map out where the single-walled carbon nanotubes are within materials using fluorescence. It's interesting. And then I'll look at discuss some of the research that I've been doing, trying to embed these nanotubes into epoxies. We'll look at dispersion. We'll discuss a little bit about alignment and strain, the effects of strain on a material, and what the nanotube does with it. And then I'll talk a little bit about a new material that we have. We've kind of dubbed it the strain paint, and might be promising in an industrial sense. There. So first of all, carbon nanotubes. That's kind of that's not an actual picture of a carbon nanotube, right? But it is actually a semi-empirical calculation of what a nanotube would look like. Diameters, they're typically around 0.6 nanometers up to 3 nanometers. They can be as large as you want, actually. Because what it is if you take a sheet of graphene, you know what graphene is? I'll show a diagram of it. It's just like one sheet of graphite. It's a bunch of hexagons. Carbon atoms arranged in hexagons. You roll that up, you have a tube. And that's what a nanotube is. Not necessarily how they're made, but that's essentially what it is. Typical lengths are on the order of about 100 nanometers to 10,000 nanometers. Of course, 10,000 nanometers is about 10 microns. One of the difficulties with carbon nanotubes, one of the hopes was that maybe you could make them very, very long and use them as wires, or use them as portals where you could transport things between. Because anything inside is not going to react with anything on the outside. Although that's been a bit of a problem, is manufacturing nanotubes when you get certain lengths. But measurements of their tensile strength, is 50 times greater than steel. So they're very, very strong. If you try to stretch a carbon nanotube, you can apply a force 50 times greater than what you could do to steel of the same dimension, and it would still not break. So it's pretty impressive. Surface area is incredible. A lot of surface interactions will occur, but it's every single carbon atom is on the surface of an nanotube. So it's not like you're dealing with a bulk material where all you're dealing with is the surface atom of that material. With nanotubes, if you interact something with a surface, you're interacting with all of the nanotubes, all of the atoms of the nanotube you are on the surface. And they can come in different types. There's metallic carbon nanotubes, and there are semiconducting carbon nanotubes. The ones that fluoresce are the semiconducting ones. The metallic ones are interesting for their electronic properties. But especially the tensile strength, and of course, made of carbon can bend very easily. So if you can find a way to put these nanotubes inside materials, you might be able to increase the strength of those materials and have a very flexible type material. So there's a lot of interest in trying to develop nanocomposites composed of nanotubes, just for the sheer mechanical properties that you would gain. There's estimates that by a few orders of magnitude, you could increase the strength of the material if you can get them embedded correctly in certain types of epoxy or polymers. Well, this is a very brief milestone in carbon nanotubes directly related to my research. 1991, carbon nanotubes were discovered. They were first discovered multi-walled nanotubes when they were looking at buckyballs. Everybody knows what a buckyball is? Buckyball is 260. Imagine a soccer ball where all of the vertices of the soccer ball have the carbon atoms. You have 60 carbon atoms in there. And two people from Rice University, Rick Smalley and Bob Curl, as well as somebody from, I forget what university it's from UK. Curl, Smalley, and name escapes me. Anyway, the three of them won the Nobel Prize in chemistry for the discovery of the buckyball. Well, in Smalley's lab, they were also able to make nanotubes. Now, they were first discovered by Ajima in Nature in 1991, and in 1993, single-walled carbon nanotubes were actually discovered and made. And there were two papers that were published back-to-back. If you look up Nature in 1993, these papers are one right after the other. They did that on purpose, so both of them get credit for discovery. And fluorescence of nanotubes, or the semiconducting nanotubes, was discovered in 2002 at Rice in Bruce Wiseman's lab. And Rick Smalley is an author of that paper also. It's interesting, they had made carbon nanotubes in third floor of the Space Sciences building at Rice University, and they took them down to Bruce Wiseman's lab. He had been doing fluorescence, and lo and behold, they fluoresce, so you could actually see them. But they don't fluoresce in the visible, they fluoresce in the near infrared. So here's carbon nanotubes that you can envision them as just an individual graphene sheet rolled up in the form of a tube. And you can imagine there's a variety of ways that you could roll these up. You have to connect one carbon atom with another and roll them up. But you can roll them up with different chiralities. So there's a bunch of different ways that you can roll up nanotubes. Single-walled have one wall. Multi-walled are actually a whole bunch of single-walled nanotubes all sharing a common axis. So each one within another. There. I found that transition. If you roll up a graphene sheet, a whole bunch of different ways that you can roll them up. If you just organize them by rows, by columns and rows, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0. If you take this 5, 0 hexagon and roll it up to a 0, 0 hexagon, the original, and you take the whole graphene sheet and sort of cut it out there and you roll it that way, you will be making a 5, 0 nanotube. I'm going to show you a 9, 4 nanotube. So say you wanted to make a 9, 4 nanotube, and each of these different nanotubes have different diameters. different circumferences here. The roll-up vector is basically the circumference of the nanotube. So if I take 9,4 and I wrap that around, matched up with 0, 0, and make sure that they connect just right, then I can create a 9,4 nanotube. So we have the roll-up vector. That's basically the circumference of the nanotube. And then we can talk about the roll-up angle. This angle is the angle from the zigzag. I'll show you why they call it zigzag. But one end is zigzag, one end is armchair, and there's a whole bunch of other nanotubes in between. That roll-up angle will vary from 0 to 30 degrees, but will not be more than 30 degrees. Once you get larger than 30 degrees, you're basically recreating another nanotube that's already within the 0 to 30. So zigzag is 0 roll-up angle, armchair nanotubes are 30 degrees, and the nanotube axis would be perpendicular to the roll-up vector. If you can imagine the roll-up vector, take that wrap it around, that makes the circumference of the nanotube, and the nanotube axis runs along that vector. So here are 3 different nanotubes. First one is an armchair nanotube. You kind of see how these carbon atoms are arranged. That has an angle of 30 degrees, roll-up angle. And then the zigzag is 0, and then an intermediate here. So if you kind of just line out the carbon atoms, you can kind of see how that's an armchair. If somebody was sitting in there, you have 2 rests, armrests on the side, so that's why it's called armchair. The zigzag looks just like that, like it zigs and zags if you follow the carbon atoms. And then if you look at it looks like this should be 0 and this should be 30, but when you look back at the actual graphene sheet that you're rolling up, it turns out the zigzag is 0 degrees and the armchair will be 30 degrees. And then the last one is one of those that would be intermediate between zigzag and armchair. Okay. Well, it turns out, let me go back.
Actually, what is this bonding?
The bonding, it's pi bonding. I think it's sp hybridization. So you're basically connecting. It's exactly the same as what graphene would be. When you roll it up, you're just connecting the carbon atoms. So you end up with hexagons. There's no pentagons. Once you form a pentagon, you start changing the shape. So that's when you start getting curves, just like a buckyball, pentagons, which actually make it rotate around. So on the ends of carbon atoms, you may get something a little bit different. But along the sidewall, it's all going to be the hexagons. Every nanotube here that's in red is a metallic nanotube. And you can identify different nanotubes by the NM number. So 7485 would be metallic nanotube, whereas everyone that's in black is a semiconducting nanotube. And how you can figure out whether it's metallic or semiconducting is subtract NM from each other, divide by 3. If you don't get a remainder, it's a metallic tube. If you get a remainder, it'll either have a remainder of 1 or 2. So you have mod 1 tubes and mod 2 tubes. Mod 1 and 2 are both semiconductors, but they both behave differently under strength. One shifts one way, one shifts another way. I'll discuss that. Metallic tubes do not have a band gap and therefore are not semiconducting, and they do not fluoresce. Okay. So okay. What's curious about the semiconducting nanotubes, those that are mod 1 or mod 2, is that the density of state at certain locations becomes very close, well, not quite infinite, but close, becomes very high, and other locations becomes very small. For the metallic tubes, there is a continuous number of states. There's at least one state for all energy levels, the valence band and the conduction band. For the semiconducting tubes, though, you end up with exam low singularities, and you actually end up with an energy gap between the valence band and the conduction band with 0 density of state. So they act like electronic transitions. So you can have
see if this comes up. There we go.
So you can have an energy difference between the highest valence band and the lowest conduction band. And the energy difference there is called P11. That is the fluorescence transition. Turns out that the lifetime of an electron at Cn at C1 is on the order of picoseconds, which is a fairly long time. So it takes some time to drop to the valence band. And that is the fluorescence. Well, how do you get the electron up? Up there is you can excite it. You can either directly excite it with an energy to P11 or with energy to P2. And because these aren't exactly energy levels, you don't have to have the exact energy to excite it. So you can have an energy around P2. Or D33 is a possibility. Turns out P2 is indivisible. Pretty much indivisible to a little bit into the near infrared. E11 almost entirely is in the near infrared. So you can detect these in the near infrared. And this energy gap is different for each different type of tube. This kind of is a visualization for larger diameters, the energy gap is smaller. Okay. So if you excite with a laser of a particular wavelength, it turns out that you will get emission at a separate wavelength, depending on what the E11 transition is for that particular type of tube. Each of those peaks are different types of nanotubes on there. So this is a plot of excitation wavelength from 300 to 800 nanometers, emission wavelength from 900 to 1500 nanometers, and that's in the near infrared. So each of those peaks, in the third axis, each of those peaks corresponds to a particular nanotube. And if you plot those peaks on a two-dimensional plot, this is what you get. You identify every single peak. So 7.6, using the process that is used at Rice University to produce nanotubes, 7.6 is one of the most abundant species of nanotubes. 7.5 is probably the next most abundant. But what's interesting is if you, say, have a 650 nanometer laser, like this one. Okay, 650 is still in the red. If you excite, you need a little bit more power than what this one has. But if you excite at 650 nanometers, you can excite 7.5 and 7.6 and probably 9.5 and 10.3. You can excite all of these nanotubes that are close and around that region. Actually, you can detect from 6.5, you can detect 10.2, 8.3. You can excite different nanotubes. If, say, you want to excite 10.5 and 9.7, you would use a laser with a wavelength of about 780 nanometers. So you can probe each different type of nanotube by using a different excitation wavelength. And you can divide all these up into two different categories. Notice all of the mod 1 tubes are below this dotted line, and all of the mod 2 tubes are above the dotted line. What's also very interesting is under strain, you're kind of stretching the nanotube out, so there's some chirality to it. You're actually stretching it to make it look more armchair-like. This dotted line would be, if they were semiconducting, that's where the armchair nanotubes would be. Notice that all of the nanotubes that are close to 7.6 differ by 1, 7.5 differ by 2. So all the ones that are close to armchair is going to be when N and M equal each other. So they will move towards armchair. So this 7.6 peak, if I apply strain to it, it will actually move towards the armchair level. The further away it is from armchair, for example 10.3, the greater the shift. And if you're looking along the emission axis, what you'll see is you'll see a blue shift. So if you're exciting right around 650, say you're looking at 10.3 or 7.6, you'll actually they shift this way. But if you're only detecting their emission wavelength, it'll look as if it shifts to the left on this diagram. it'll be blue shift. But if you're looking at a Mod 2 to 7.5, for example, it'll shift to the right. It actually shifts down. So it'll shift down and to the right. So it'll red shift. So what's really interesting is when you apply strain and you have different types of nanotubes in there, some will blue shift, some will red shift. And the response to strain is linear, it turns out.
It's pretty neat.
So here's the nanotube fluorescence microscope system. That's that right. It's an inverted microscope, Nikon microscope. You make sure you do not look through it. When you have lasers exciting nanotubes on there. But the sample is put right up here on this little ledge here, and a laser, there's a whole bunch of lasers set up that optically come in this way, reflect down, you excite the nanotube material, whatever you're looking at. You can put it on a glass slide, or you can have the material sitting right there. You excite it, the material gives off, so the nanotubes will fluoresce. That fluorescence will be captured, and you have a filter down here to block out the laser wavelength. So all you need is a long pass filter to cut out the laser wavelength. That way you can excite with a shorter wavelength, and then you can observe the fluorescence, which is a longer wavelength. And once it goes through there, you can send it to this detector on the left, which right now is cooled by liquid nitrogen. This is a two-dimensional indium gallium arsenide detector, and it's actually a camera. So that's stuff through the computer, you can actually see a near-infrared fluorescence image of nanotubes. What's really neat is if you have the nanotubes in solution, say, on a glass slide, you can feel the grounding motion. It's like these little tiny worms are moving around it. I don't have any videos of it, but I do have a picture. On the other side, there's a one-dimensional in-gas detector, which allows you to detect the spectrum. So what you can do is you can actually position your sample so that you look at one individual nanotube. You can image a bunch of different pixels. This is a 83,000 pixels here. So you can image a very large region, but you can see all of these individual nanotubes. And you can position your nanotube at a particular pixel, and then the spectrograph can be directed so it'll pick up the spectrum only from, well, not quite one individual pixel, but about 5 pixels, 5 or 6 pixels. So you can position your nanotube right at that one particular spot, and you can pick up a spectrum of an individual nanotube. As long as there's no other nanotubes close, it'll be a pure individual single nanotube spectrum, which is pretty impressive. I was able to get a spectrograph like that here. So now I can actually look at bulk spectra using that. Well, this is some of the work that I've been doing. I've been trying to put nanotubes, single-walled nanotubes inside materials. And this is an example of nanotubes. They're fluffy, very fluffy. You see the dark in there. I'll pass this around. Just don't open the cap. Probably not going to do anything, but I don't want any wind current to flow and we get nanotubes going in there. So I take a little bit of nanotubes, just a pinch. Very hard to measure this because I'm looking at microgram quantity putting in the solution. I first looked at single-wall nanotubes in PMMA. If you don't know what PMMA is, everybody knows what plexiglass is. One of the first polymers ever made. Plexiglass is PMMA. Polymethyl methacrylate. You can put this in solution in toluene, and I use PFO as surfactant, and this is PFO. I'm not in the chemistry aspect, so this really doesn't make a whole lot of sense to me, other than I know it's got carbon and chlorine and oxygen. So, anyway, everything like this. But this particular surfactant is very good at wrapping itself around nanotubes. And a surfactant has a hydrophilic side and a hydrophobic side. Well, surfactants that are soluble in water are, such as SDS, sodium ledecyl sulfate. You probably have seen sodium lauryl sulfate, an ingredient on detergents, shampoos. Surfactants, what happens is one part opposes, wants to get away from the water, the other part wants to be beside the water. That attacks the dirt, attracts dirt, and then you actually pull dirt off your clothes. That's how the detergent works. Well, it turns out with a surfactant, you can overcome all that bundling. If you look there, there's lots of nanotubes there, and they're all conglomerated together. There's very large van der Waals force of attraction between nanotubes. The surfaces just, they come together and they stick together, and it's very hard to separate them apart. If you want good dispersion inside materials, you've got to be able to separate out the nanotubes. That's one of the biggest difficulties, one of the biggest hurdles that material scientists are trying to jump over. That's very difficult, very, very difficult. So using a surfactant is one way to separate out the nanotubes, and then you can hold these in suspension for a while. So I took this in, I used toluene, put the CFO surfactant in a solution with toluene, and when I allowed the material to cure, the toluene evaporates, and you're left with individual nanotubes with PFO surfactant wrapped around it inside the material. The other epoxy that I've used is the Epon 862, or 826. I use 826 and then use 862 without a surfactant. This was a difficult material to try to build. Even this curing agent attacks the nanotubes and just kills fluorescence in the nanotubes. So that wasn't the best material to use. But another material which is interested, which the Air Force is interested in, is this Epon 860 that they use a particular curing agent. If nobody knows about, does everybody understand about epoxy? Everybody use epoxy before? And you buy the fast curing epoxy, usually there's two tubes. You push the two tubes out. The one tube is the resin, the other tube is the curing agent. And when you mix those together, then you end up with cross-linking between the curing agent and the resin, and it forms a very hard object after it cures. The idea is if you could make epoxy, which is already fairly hard and with lots of properties that are positive properties, if you could put carbon nanotubes inside it, then you can make it even better, even stronger. Well, with PFO surfactant, I get good dispersion. It's wonderful dispersion. The nanotubes are separated out, incredible. And I was able to investigate the strain on individual carbon nanotubes. And I'll show those results a little later. But we also found, I didn't like the results. So the CFO is not dealing with carbon nanotubes directly in contact with the epoxy. Then you have this surfactant layer in between. That causes problems. So I tried doing it without the surfactant, and this bundling is a big, big problem. And once you start getting the curing process take place, it becomes the viscosity drops, and the nanotubes can move around all over the place, and van der Waals forces just bring them together. Incredible. So we developed a method to try to prevent aggregation with that. And this is basically how I did it. You take single-walled carbon nanotubes, just like it's in that jar, add them to your epoxy resin or a surfactant solution, and you have to use ultrasound in order to agitate it enough to be able to separate out the nanotubes. And that's using tip ultrasonication. So it's a little tip, it's an ultrasound pulse, and we did it at about 10 watts per 10 to 30 minutes. It all depends on the material that you're using. But that's what's used to debundle carbon nanotubes. If you just put those nanotubes in the material and try to mix it, you'll have globs of nanotubes. And the positive contribution to the material is going to be completely negated with having all those bundles in it. So what's important is to tip ultrasonicate, get it, mix the resin and curing agent, pour it into molds, and get it to cure as soon as possible. This particular material that I was using, the Epon material, you had to cure it at 120 degrees Celsius for 4 hours. So after the first hour, after 1 hour, the viscosity drops incredibly, and that's what allows the curing agent and the resin to cross-link and bond. But that also allows the nanotubes to bundle, to rebundle. So we would end up with lots of specks inside. Not good for the material. So without the surfactant, you end up with rebundling of the nanotubes. With the surfactant, you end up with the carbon nanotubes slipping inside the material, which means they don't really transfer any load to the nanotubes. Here's how I made some of the thin film. I used Teflon-coated slides, and I would drop my material right in between there, and then put this in the vacuum oven and heat it up. Titanium foil, and I would end up making a film. This is an example of what would be in there. So the film that I was trying to make was right in between there. One of the problems, though, when the viscosity drops, it just becomes very, very liquid, very fluid, and so you end up forming film in between every crack and crevice inside the bowl. So another way that I did it was to try to pour all of my mix of nanotubes and epoxy and resin on one side and have it flow into in between two sides, which is a piece of material in order to make a thin film. With PFO, it was great. I could make nice thin films out of it. Without a surfactant, it's pretty difficult. Here's an example of PFO. This is PFO in toluene. This is taken with the near-infrared imager, the two-dimensional array that I mentioned before. Each one of those bright objects is an energy. One pixel is about 0.3 microns. That's about the resolution you're looking at. So this particular nanotube, it crosses about 5 or 6 pixels. So it's probably about 2 microns in length. And some of them will be long. I think the longest one I've seen is about 10 microns. One of the difficulties with the separation process, another difficulty, is when you tip sonicate, you break apart some of the tubes. You make them smaller. So now you're dealing with, it's good that you get rid of some of the catalyst that's in it, but then everything is a very, very small tube, so you can't hold on to long tubes that much. Here is my nanotube inside the material. This is a cured material of Epon A62 of curing agent W, but with a surfactant wrapped around the nanotubes. And the surfactant you can't see, but you see the fluorescence of the nanotubes. You can see that they are individual tubes. I could look at that particular one, and actually, this is not the section with that one, but I did collect data on that particular nanotube, right on there. It's a 10-2 tube. So a 10-2 is far enough away from armchair that you see a nice big shift when you look at it. And this is an example, this is an 8-6 nanotube. So when you look at the spectrum of an individual nanotube, you get a nice peak right at a particular wavelength. And you can fit this to a Gaussian curve, and you can figure out where the peak is. Exactly. Okay. How we applied strain to it, this is a device built by some graduate students initially at Rice University. They went on to work at Johnson Space Center, and now they are in Korea. But the way this works is you coat the material on top of a PMMA bar, a plexiglass bar. And you put that bar inside this little device. When this screw is turned, it'll push on a particular, on this plate right here, and it'll bend it down. It'll cause this square piece, which has 2 rods underneath it, to push down on the material. So you end up with these 2 pins pushing down, and then 2 ends hold the material stationary, so you end up bending the material. When you bend the material, you're creating strain. And then the surface, the film on the surface, will have essentially the same strain as the substrate. It's so small that it essentially has the same strain. Although we did put strain gauges on the film and on the PMMA just to make sure that they were the same. They're pretty close. We put a strain gauge on there so that we could actually measure the strain. That's how strain is most commonly measured, is using a strain gauge. Have we seen that before? There's 2 wires that are attached to it. These are how along the edge of that bar. They just measure the change in resistance. As the strain increases, the wires in the strain gauge become smaller diameter, and that increases the resistance. Yeah. The change in resistance is proportional to the strain. So that's how we measure strain. It's optically transparent, so that we can shine a laser directly on our material and detect the fluorescence out the other end. Or you could make it so you detect the fluorescence coming back. You can either do it with reflection or transmission. So here's an example of what happens to the nanotube under strain. Under extension, you'll be stretching the nanotube, so it'll move towards armchair. And when under compression, you will be kind of squeezing it together, and you'll see a spectral shift in the opposite direction. Okay. Well, here's some of the results that I obtained. These are two individual nanotubes. Both of them are 10 tubes, and both in the same material. This one is, I can tell what the alignment is. The polarization of laser, you may not know it, but a laser has polarization to it. The electric field is aligned with one particular direction, or you can pass it through a polarizing filter, and only polarization of a particular angle will get through. But if you change the polarization of the laser, you can determine the alignment of the nanotube. This is the nanotube. The polarization of the laser, if it's in the same direction as the axis of the nanotube, you'll get bright fluorescence. But if the polarization is perpendicular, you get almost zero. So just by changing the polarization of the laser coming in, you can determine what the alignment of the nanotube is, just by doing the fluorescence. So that's nice. I was able to determine exactly what the alignment was. This was 20 degrees away from the strain axis. This was 36 degrees from the strain axis. But they're both the same type of tube. You would expect that the shift under strain should be pretty similar. I mean, 20 degrees and 36 degrees isn't that far away from each other, the alignment. But the slope is incredible. I really tried hard. With each tube, you have to look at one particular tube, and then you adjust the strain for that particular tube. And sometimes you lose the tube, go back and find another one. So I've tried hard to put this on the same horizontal and vertical scale. Those two are on the same scale. But this has a much steeper slope. The shift right here, which was about 1072 up to about 1084, so that's a shift of 12 nanometers, whereas this was from 1072 to about 1081, which is a shift of only 9 nanometers. So the individual locations of the nanotubes within the material plays a role. They have different alignments, and depending on the wrapping of the surfactant, they could have a different amount of slippage. But you can actually study the slippage of nanotubes within the material. Okay. Now this is the second, the one that was on the bottom right. That's this tube. This is increasing strength. Increasing strain, and then I tried to look at what happens to the shift of the emission peak, decreasing strength. And increasing it is fine, it's pretty much linear, all the way up. The problem is decreasing it, there's a little bit of history. It started to come down, and then it just took off, did something wild, and then it completely disappeared. And what happened was, the way that strain was applied, the standard material was moved out of the optical plane, and I have to refocus to get back in. Well, to refocus, you also have to refocus the laser that's coming in. You're focusing a laser, and you're detecting it using an objective to a microscope objective at the other end. So you have to refocus both things. If you focus it too tightly, then you end up with a huge laser intensity being absorbed by the nanotubes. Nanotubes are black, you can tell. So when energy and the laser hits them, they will absorb it. So if you put too much intensity on there, then it just absorbs it completely, and it can actually explode. It's called photo bleaching. That's what happened right there. Just prior to photo bleaching, though, it went through all kinds of contortions. So the structure just started twisting and changing all over the place, so I didn't get any normal response to that. But if I could have kept the laser with the same intensity as far as what the tube was seeing, I would have seen this come up linear, and it should have come back linear. And that's what happens with those tubes.
I'm really confident in this being history.
Say that?
Really confident in this being history.
There is some hysteresis with these individual nanotubes. Prior people right, actually put nanotubes into PMMA solution, and they did a study on that, and they saw hysteresis on all of them. A little bit of hysteresis. So if I brought it positive and came back this way, I should be able to bring a negative and come back again. And there's a little bit. That's one of the other things about detecting using nanotubes to detect strain. You want to have a material where if there is any hysteresis, it's almost non-existent. You want to try to limit the hysteresis as much as possible. Here's another tube in that material, and after looking at this, I decided it wasn't really doing what I wanted it to do. The nanotubes were not going to improve the strength of the material. I applied strain all the way up to 0.9% and got nothing, no shift at all. After 0.9%, though, all of a sudden, I guess the material had grabbed on the material and started stretching. So inside this material, it was just, this tube was able to move around fairly easily. And it could have been the PFO surfactant, it could have been the PFO that was slipping inside the material, it could have been just a cavity in the material. I think it had to do with the PFO because I saw this happen with a lot of tubes that saw one slipping. So here it's slipping all the way along here, and then suddenly it grabs on. This should normally be the slope with strength. So I should have seen the slope from here, should have gone straight like that. But because of the PFO surfactant, I got some slippage in there. What's interesting is that you can actually study individual nanotubes and determine, are you really transferring load from the host to the nanotube, or is the nanotube kind of slipping a little bit? You can look at individual nanotubes and you can study them like this. So moved on to this material without a surfactant. And we were making samples using a vacuum oven, heating it up to 120 degrees. And after 1 hour, the viscosity drops incredibly, and aggregates started forming. So our solution was, let's get rid of this vacuum oven. And let's see if we can get right to the point where this viscosity drops, and then it drops, and it's very liquidy, and then all of a sudden it hardens. Very interesting type of the process. So we replaced that with a hot plate, and just sort of warmed everything up to the right temperature, and then tried to pour our mixture right on molds that were already heated, so that we could get it to cure as quickly as possible. And it worked. We did get nanotubes separated. So this is the idea, very simple. Didn't use a vacuum oven, didn't have to wait for an hour to cure. We took 2 plates, put the material down, put the plate right on top, had it all heated. The setting on the hot plate was 300 Celsius. We couldn't really tell exactly what the temperature is if you've ever used hot plates in a chemistry lab. You know, the setting that you set it on is lower, is usually a higher number than what the real temperature is. So it was above 100, probably around 200 Celsius, where the material was. And then we had it cured right away. And it was really interesting. For first 3 to 5 minutes, that's where the viscosity dropped. After 5 to 7 minutes, suddenly the viscosity increases. And that's when the nanotubes start staying in their places and they're not going to be migrating out. After 10 to 12 minutes, you still have a high viscosity, but at this point it still could be molding, so it's plastic-like. Result was plenty of individual nanotubes and very few bundles and aggregates, which was great. But the problem is when we actually tried to apply strain to these materials, we saw no shift at all. Part of the epoxy, the way it's cured, the special way it cures at 120 Celsius for 4 hours, and then you're supposed to be post-curing for another 4 hours after that. There's a particular procedure. Each epoxy has its own type of curing process, and we were circumventing that, and I don't think we got a very strong material as a result. But maybe we'll be able to find some way to be able to cure that beyond that point. Maybe get it harder. But we did see individual nanotubes. And we could look at their spectra. This one, you can look at the fluorescence spectrum and determine what the peak emission is, determine that it's an 8-3 tube, that's an 11-3 tube. Those are very far from armchair. Those would be great to look at the strain effect, but you should see very high shifts for nanotubes that are further away from armchair. So another part, sort of changed gears a little bit for my research. Instead of looking at individual nanotubes and looking at the strain effects on them, I'm trying to figure out a way to align nanotubes within materials. So if I can get them dispersed, maybe I can get them aligned, because there's certain properties that will be very beneficial if you can line nanotubes all up. Electrical properties, thermal conductivity, as well as just strengthening materials. If you have them all in a particular line, then bending it along that axis that they're aligned with, you'll have a very strong material that way. So I looked at magnetic fields, flow, and electric fields, and magnetic fields is kind of interesting. Here's the nanotube sample. This is a magnet. Attached to something metal and sticks that you use for an office table. But take a look at it. Yeah, I can hold that. Yeah. They appear to be magnetic. So if I put a magnet on there, it would be magnetic. You should have magnetic properties, right? But they're carbon. Does carbon have magnetic properties? It's not just carbon. The Withey process, which is the process developed using iron as a catalyst to make the nanotubes. Turns out that you need some sort of a catalyst in order to cause nanotubes to be formed. And the thinking is that if you have an iron particle, which might actually have a carbon inside the metal, kind of it's soluble in iron. Carbon is soluble in iron. It's almost like a solution of carbon atoms within iron, within that particle. And then the carbon within that iron particle will attach themselves 2 by 2. We think it's 2 by 2. And then that's producing a tube. So it grows from the particle out. You end up producing this nanotube. So on the ends of every single nanotube that's grown, you'll have this iron particle. In the Withey process, you're actually making your iron particles beginning with elemental iron, individual iron atoms. So you're growing this iron particle, and when it reaches a certain size, you've got carbon mixed in, you grow a tube. This all happens in vacuum, so it happens along a flow inside a big piece reactor. So once the iron particle becomes too big, then the tube stops growing. So they're only growing to a particular way. There's other methods of growing nanotubes. Molybdenum is used. Cobalt is used. So there's different processes, and everybody has their own patents on how to make nanotubes. Some people think they have a new patent, so they bring their samples to the lab at Rice, and they tell them, sorry, there's no nanotubes in there. At least they're not single-walled. But inside here, there's iron particles. During this hip sonication process, a lot of those particles will break off because you're breaking the nanotubes to the end. So we tried to apply some magnetic field to materials with nanotubes in it during the curing process, and then we looked at the alignment of these nanotubes, and we saw no preferential alignment at all. So if you don't have an iron particle, or even if you do, and you put it in a magnetic field, the iron particle will rotate, maybe, and align itself along the magnetic field line, but the attached nanotube is just going to be curled up around it. It's not necessarily going to be oriented in a particular direction. So we saw no preferred alignment applying magnetic fields to it. Now, apparently, there have been some experiments with very high magnetic fields. There's a 20 Tesla field that's been created at the University of Florida, and some materials have been shown to have nanotubes line up in that direction with very high magnetic fields. Whether that's an effect of the metal catalyst in there, or whether that's an effect of carbon nanotubes, a property of carbon nanotubes itself, I'm not sure. The other way that we tried to line them up was using flow. And it's difficult to try to figure out how we can make a thin film that flows while curing at a high temperature. So it's at a high temperature, so you have a certain size. You can't just let it flow down a big, huge, long column. So one of the ways to do it is to drag something across it. There's been evidence that a nanotip could be used. We just kind of makeshift with a pipette. And we did see some evidence of enhanced alignment. of nanotubes. Not that much with this flow, but maybe there's some other ways that we can look at increasing the flow rate while this material is curing. The other way we looked at it was using electric field. And there's still more work we need to do on this, but we did see some evidence of alignment. I'll show you that in a second. 2,000 volts were applied across a 2x8 foil sheet, and they were sandwiched between 3 PMA bars. And then we poured our solution right in between. We wanted to see if they would line up along the electric field lines to produce the chemical. And we did see some. If you look in this diagram, this is an image taken from the two-dimensional near-infrared camera. There's two little white dots here for the fluorescent nanotubes, which at a particular laser polarization, you see almost no intensity. 90 degrees away, both of them end up becoming more intense. So that's evidence that both of these two nanotubes are aligned in the same direction. So to change the polarization and all of the nanotubes, and what would be really nice is that every single nanotube here is not fluorescent, but is fluorescent. If that's the case, then we would know that they were all oriented in the same direction. There may be possible we may have to do some more experiments to figure out how, during the curing process, we can align all of the tubes, or maybe just more than 50%. My goal is if I can get 50% aligned, that would be great. But there's clear evidence that there is some alignment going on if it's 90 degrees away. Yeah.
You can't use that kind of the kind of magnetic property that you were showing us, the iron, to kind of align them that way?
That's one of the ideas I was thinking, was to use that, but what will happen is the iron particle will just rotate itself. If you've ever seen iron filings, put iron filings in a magnetic field, they don't move along the field lines, they just rotate themselves and orient themselves along the field lines. Now, nanotubes will rotate themselves along the electric field lines, but if the electric field is high enough. And I'm not sure if there's a difference in metallic tubes and semiconductor tubes as to which will align more or less. Yeah.
Do you ever have polarimetry of the emitting phases, or is it the one?
On what's emitted?
Yeah.
To determine whether that light is polarized?
Yeah, if that's polarized, then we can measure the orientation of the tube perhaps, and we could have a direct measurement of the orientation.
Okay, but this already gives me a direct measurement of orientation. If I have my polarization along here, let's say this is 0, I don't see any intensity. I rotate 90 degrees, I see intensity. I can actually plot this and get a nice line curve.
Well, I guess if we could measure all the orientations at once, it'd be like illuminated as an unpolarized light, polarimetry on
Right.
the
Okay, yeah, and we could do that. Yeah, we could do that. Have it completely
I
unpolarized.
don't know how much we have there, polarimetry, so it looks like.
Yeah. Yeah. It's not real intense, and you can't see it with your eye, of course. It's a laser light, you can't see it with electric light. And you have to detect it using near-infrared. But there may be a way to put a polarizer on the other side. Do that. That's what you're saying, right?
Yeah, I don't know if it's polarized, it could be unpolarized, I don't know if we can expect that.
I'm not sure. I think it's unpolarized. Because what you're doing is you're exciting electrons up, and it's just falling down the band gap, so it's giving off a photon, and it's not necessarily in a
Well, within
particular
a
direction.
laser,
But it could be.
something similar is happening, and that's all polarized.
Yeah, it could be.
In the same orientation. I mean, in the simulated mission there, the polarization is all.
Yeah, that could be interesting.
Of course, it could emit polarized with a beam, and then you're just getting your polarization stays the beam,
Right.
which is not what else.
Well, I know that nanotubes that are laying flat on the surface will emit light out in the cone. So and then we have to focus that back into the detector. If you don't focus it, you really get low effect. So, but still, they might have slightly different orientation, so. Yeah, okay, keep that in mind. And then I'd like to move on to a new material that we've got. You don't want all of the nanotubes aligned. You would rather have them mixed, but they have to be individual. If these nanotubes are touching each other, then you won't see any fluorescence. You can't detect the nanotubes. Then you have to use something like Raman spectroscopy or something else, which there are some problems with that. The fluorescence spectroscopy is really easy as long as they're separate. But this is our method of detecting fluorescence using in a material that we dub strain paint. Say you have your material, you have randomly aligned nanotubes inside. You put that on a test plate and put it in a strain paint. This one doesn't quite look like the same one we had before. We're hoping that if we construct something like this, we can actually strain it without actually bending material. That way it doesn't go out of focus and you don't get these artifacts. But all you would need is an excitation laser that you could polarize and excite. And then you can see the fluorescence coming back this way. And of course, you put a long path filter in there so you don't get any of the laser light coming back. And pass it through a fiber collimator into your spectrometer. This is a device that you can actually construct and make it, you can go back there. If you could make a strain paint, a material that you could just sort of like paint on the surface of the ingot, then you could use the fluorescence coming from the nanotube to detect the strain without having to connect a strain gauge to it. Okay. And this is what we see. If we embed carbon nanotubes in polyurethane, we tried a few other substances, but this one, so here's an example. You can pass that around it. Just a polycarbonate slide and some of the strain material on it. You can't see the nanotubes in there because the concentration is very low. It's about less than 0.02 weight percent carbon nanotubes to the polyurethane. But when we apply strain to this material, we actually do see a shift. So here we're looking at a bulk spectrum of nanotubes. This piece here is a 7.6 piece. This is a 7.5 piece. 7.6 is mod 1. So under strain, under positive strain, it goes from the black line to the red dashed line. So under positive strain, it's blue shift. So it starts right here and it shifts over here at 0.55% strain. Not very large strain, but you still see a shift. 7.5 does the reverse. It's red shifting. So we see 7.6 blue shifting, 7.5 red shifting. These peaks, even though you can distinguish them, and you can fit them to curves, you can determine their peaks fairly well, you can get an even better measurement if you subtract the distance. Because under positive strain, they're moving in. On the negative strain, they'll move apart. So if you subtract the two, you basically double your shift that you would measure for any one tube. They don't shift exactly the same amount because they're different. It depends on the cosine of 3 times the roll up. So it depends on that. But you can clearly see a shift there. And also you can see some other bands. This is the 9.5 band, but there's some other nanotubes kind of under the envelope there. And this is 8.6. Right here is 10.2, and here is 9.1. So it's very hard to determine exactly how they're shifting. So if you stick with just the two, 7.6, 7.5, you can actually see a shift. If we could select just 9.5 and 8.3, 9.1, I think is where it would be. Or 10.2 and 9.5, they would shift even more, and the shift would be even more pronounced, would be even easier to detect. If we look at what happens under loading and unloading with this material, we start looking at the 7.6, 7.5 separation. Loading, separation decreases. They're moving together. One's blue shifting, one's red shifting, moving together. And then under unloading, they come back. There's a little bit of hysteresis, but almost non-existent. So we could use this as a calibration. Take the material on that surface. Once we calibrate it, we can look at it later and just look at what the shifts are, and we can figure out what the strain is on that material. One of the difficulties that they're having with airplanes right now is trying to determine the strain in microcracks. Well, this could be a material that you can just paint on the surface of an aircraft wing and detect microstrain, like up to about 1% strain, and any places where you see high strain, investigate that for microcracks. It could be a step before you actually get to that point. And there have been airplanes, what was it, last year there was an airplane fell out of the sky because of that? Or a couple of years ago, that was an Air France plane. So, the other thing you can do with this is your laser, if you have it polarized, you can change the polarization of the laser. And you can detect strain in multiple directions. So, if you start at a particular polarization, it's a 7576, and just change your polarization angle. This is 0 degrees is along the strain axis. If you go 90 degrees away, if it's stretched in this direction, and you put your polarization axis perpendicular to it, the nanotubes that are aligned that direction will be compressed. So if it's stretching this way, any nanotube that's aligned that direction will be stretched, but nanotubes that are aligned perpendicular will be compressed. And so you'll preferentially select those nanotubes that are aligned in the same direction as the polarization axis of the laser. And this fits real nicely. Again, there's a little bit of fluctuation. There's still maybe a little bit of work to do, but proof of concept is pretty good. So if you're looking at a surface, you put your little device on there, shine the laser down, detect the fluorescence coming back, measure the strain based on just the fluorescence shift, and then change the polarization axis, and you can measure the strain in different directions. And so you can map out the whole surface without ever contacting the surface. You've got to get close to it, but you don't have to actually contact it. You don't have to destroy the surface. You don't have to connect leads up to it or put a strain gauge on it, measure it, and destroy the surface that way. So it's completely non-contact, multi-directional, and it could actually, if you've got nanotubes in the material, you might be enhancing the mechanical or thermal properties of that material too. So it really could be a in this case, polyurethane is used on a whole bunch of different devices and withstands weather very well. So this is one of the nice ideas that we've sort of stumbled across, and this is something that this is more pie in the sky, and of course the shuttle mission is a little bit gone. But the idea is if you had this coating, say on the wing, you could shine a laser and detect the fluorescence coming back with it, and be able to detect the stress going on in the wing without ever having to get out on the wing and measure it. Yeah, we've got to work on getting the detection pretty good. I don't know what density of nanotubes you have to have in there, but that may be a little bit grandiose, but you could at least measure wings and wind tunnels and put your detector close to your wing on that. But this is something that Bruce Wiseman came up with when we first were looking at this, and I thought that was an interesting graphic. The strain tank, we just submitted this to Nature Nanotechnology, so we're hoping to get a good result from it, get it published. And then these are some of the other references about fluorescence and about strain and the shift in fluorescence of nanotubes. And I'd like to acknowledge Bruce Wiseman for his generous use of all the facilities in his lab. He just kind of opened up and I said, hey, I'm interested in doing some research. And he said, come on over. And that was good. And I've had students who worked with me at my previous institution, and that was all part of the Air Force Minority Leaders Program that allowed the students to work with me on part of the research we talked about. That contract is actually being transferred over, and so there may be opportunities for any minority U.S. citizen students who would be interested in doing research with me on this. There may be some you might be able to get paid to do some of that research. So, thank you.
Thank you. All right, question?
Yeah.
How do you think that this paint would work on something like emulsion colors?
We haven't really, one of the things that we wanted to do is investigate the effect of temperature on this. We don't know what would happen with high temperature situations. And also, if the strain is too large, we don't know if it sort of rips apart the paint material. We don't know what that would do with the nanotubes inside. So I'm not sure about that, but can polyurethane be put on the propulsion belly? Can you put polyurethane on it? If polyurethane can withstand, then it should be able to work. Right now we're tip-sonicating the nanotubes and the polyurethane at the same time. We know that breaks apart the nanotubes. We don't know if it's going to do anything. If it does anything to the polyurethane, it changes its properties. So that's another thing that we're kind of working on. But if polyurethane can be put on it, and it will withstand it, then I think the reason why we couldn't do this there. That's one thing I was thinking about, was in the other parts within the airplane that really get high strains and high stresses, and go through a range of different temperatures with this material work on.
And usually these temperatures are low temperatures.
Okay.
Heat to the emulsion cases.
Right. The work. You have something to do like testing. Because we were willing to mix up a sample and put on it. We're trying to get some input from NASA, Air Force, Army, and Navy. So we should get right to really do and know how to make good contact with it. But we're hoping that somebody will pick this up and be interested in it and be able to fund us to do a whole bunch of other analysis on it.
You mentioned that the nanotubes fluoresce. I'm wondering what makes them fluoresce in the first place?
It's the band gap. I'm not sure what slide that was. This one, right there. Okay. So right there, an electron, if you excite it with E2, and that's the excitation, you'll bump an electron from the second valence band up to the second conduction level, and then it'll fall back down to C1 almost right away, and then it sits at C1 for a little bit before it actually falls down to C1. And that's what we do with fluorescence.
They only fluoresce when they're excited, right? Right.
You need to have an excitation laser in order to see the fluorescence. Otherwise, all of your electrons are going to be sitting in the valence. But if you hit it with the right wavelength, and that wavelength actually doesn't. We were using a 650 nanometer laser, which is about the same wavelength as the laser pointer. A little bit higher in energy, we're about 20 milliwatts. But we could look at different nanotubes by using different laser wavelengths. And all of the semiconducting nanotubes, which is about 2/3 of all nanotubes, fluoresce. So you won't see this for metallic nanotubes, but you will see it for the semiconductor. Answer your question.
Are you familiar with the National Research Council's latest report? NASA had a 10 to 20 year roadmap, and the National Research Council was requested to, with the National Academy of Sciences, requested to review that. And that report has just been issued. And nanotechnology is one of the major ingredients of that report. You might that report's available at one time.
Okay.
Actually, that picture of the carbon system is very interesting to me because we actually tested the carbon system on the JSC structure lab. Tried to strain gauge it because it's so porous, of course, has so many microcracks on it, which do manufacturing from coating basically. Strain gauge is really good to get a good result. So something like this might work. But you might want to get hold of that report because you can things like structural materials and incorporation of nanotubes and your strength for ablaters, it might actually increase what we call the charge strength. You want to maintain charge retention, high speed injuries, and so all of this was kind of part of this 20-year plan.
Right. Yeah. And I know with material, just getting nanotubes into a material is supposed to really increase the strength. What they've gone to now, because of all the bundling, is they've gone to functionalizing nanotubes, connecting things to the sidewall, so those can be connected to whatever material you're using. But as soon as you start doing that, you're lessening the properties of the nanotubes. You're attaching things on there. So you have to, how much are you attaching? How much of the sidewall is actually being functionalized? It becomes a big issue with that. And then the property of the nanotube begins to change also. So I know there was a lot of promise for this. The problem has been is that they haven't been able to get the nanotubes where they want them spread out evenly throughout whatever material they're trying to go into. But if you can do it, then the theoretical results are that it would be very promising material. So the NRC report?
Yeah, it's
Any other questions?
Is it possible to make a nanotube out of another material besides carbon?
Yes. There's lots of nanowires, but they're not going to have the same properties as carbon. They'll have different properties. There's a lot of research going on with nanowires. To my knowledge, I don't think that nanowires fluoresce. So, there's silicon. There could be a lot of other types of materials that are almost one-dimensional. The nanotube, I think, is most interesting.
Well, thank our speaker again. And hopefully we'll see everybody next week for our weekly talk. We're going to have John Shevlin here from the NASA Johnson Space Center, and he's going to be talking about the use of magnetohydrodynamics and actually studying the magnetic field of the Earth. So it should be very interesting.